Hello, everyone. I'm Yuanyuan Tian from the Gray Systems Lab at Microsoft, and today I'm going to share my views on the world of graph databases from an industry perspective. So first, I want to introduce a little bit about myself related to graphs. My passion for graphs dates back to the beginning of my PhD in 2003. Although I have conducted research in many topics over the years, but graph has always held a special place in my heart. In my current job role, I have been collaborating with Azure data product team and the Liquid team from LinkedIn on various graph projects. And previously, during my tenure at IBM, I was the mastermind behind the DB2 Graph, which is IBM's a graph database product. Now I've seen a lot of talks and surveys about graph databases from an academic perspective. So I feel like there's still a lack of a survey of graph technology from an industry perspective, and that's the motivation behind this talk. And I also want to declare that what I'm going to say is on my personal view. It does not represent Microsoft. Okay, so let's start with a little bit about market research. So according to a market research company called Research and Markets, the global graph analytics market in 2022 was valued at $1.14 billion. And the market is projected to grow at 34.8% and reach about 6.9 billion by 2028. So clearly, graph is a very interesting and promising area for people to work on. And in terms of customer use cases, graph has been used in many vertical industries, including finance, insurance, healthcare, security, retail, energy, power, manufacturing, supply chain, and transportation. So when we talk about graph, there are actually different kinds of graph workloads, and there are also different ways of characterizing graph workloads, depending on what characteristics you care about, whether it's latency, throughput, update rates. So here I'm presenting a very simple way of characterizing graph workloads. On the left-hand side, we have a type of graph workloads that focus on low latency graph traversal and pattern matching. So people usually call them graph queries. So they usually touch a local region of a graph, and they have a more low latency and interactive response requirement. Examples would be like finding two hop neighbors of a node or finding the shortest path between two nodes. Because of the low latency requirement, people also call them graph OLTP. On the right-hand side, we have graph algorithms, which usually involves iterative long-running processing of entire graphs. Examples are PageRank and the community detection algorithms. And because of the long-running nature, people also call them graph OLAP. And recently, there's also a new trend of combining machine learning and graph together. People call it graph ML, graph AI. Examples, graph neural networks or node embedding, graph embedding. What I often see that in practice, in industry, people often lump the graph ML together with the graph OLAP, graph algorithm together. So now let's look at the graph models. So in the graph database industry, I see two prominent graph models. One is the RDF model, the other is the property graph model. So the RDF graph is basically a directed edge-labeled graph represented by subject, predicate, and object triples. And it is often used in knowledge representation, inference, or web semantic type of applications. On the other hand, the property graph is a directed vertex-labeled, edge-labeled graph, and with vertex and edge often have a set of properties. And the application usually involves in graph traversal, pattern matching, or path or graph analytics. And one observation is most of today's graph database support the property graph model. So now let's talk a little bit about graph language. So on the graph LTP side, for RDF graphs, there is a standard Sparkle query language. On the property graph side, there's a little bit of graph chaos. There have been a lot of algorithms being used and proposed over the years. One more widely used graph language is Gremlin. According to their website, it's being supported by roughly 30 graph vendors. Another widely used language is OpenCipher. It's roughly supported by 10 graph vendors. And our hope is to end this chaos lies on the ISO standards efforts on GQL and the SQL PGQ. So I'm very glad to know that the SQL PGQ standard is already out and Oracle is adopting it. So hopefully the GQL standard will be also out very soon. So both of these standards integrate ideas from Oracle PGQL, OpenCipher, the G-Core efforts from LDBC, and TigerGraph's GCQL. So before all the standards are out, I think it's still going to take a few years for the standardization to settle down because there are a lot of applications already written in various existing graph languages. And at the meantime, if you're building a new graph database, I highly recommend you adopt the standard, or if not, the standard is not there, adopt a popular language and definitely avoid inventing a new one. On the Graph OLAP side, there's also no standard language or API, but most vendors actually support the Prego-like API. And I think this area is very similar to machine learning, where the API probably doesn't matter too much. What matters most is the built-in algorithms. So this is the graph technology landscape in 2022 created by memgraph. So it's actually like a tree. There is a categorization. And if Leaf Node is actually a graph technology company. So clearly this graph space is very crowded. And the market is also pretty fragmented, represented by many small-sized companies, medium-sized companies competing with each other, as well as competing with the large enterprises. So move on. So as a result, I cannot possibly list all the graph offerings today in the market. So I'll highlight some of the major offerings in 3 categories. Graph-only vendors, major data companies with graph support, and enterprise cloud companies with built-in graph support. So in terms of graph-only vendors, the top contenders are TigerGraph and Neo4j. For major data companies with some graph support, we have DataStax and Databricks. In terms of enterprise cloud companies, the competitors are Amazon, Microsoft, Oracle, and IBM. And Microsoft actually has 2 graph offerings. Now let's take a look at the different dimensions. In terms of the deployment, most of the vendors have both on-prem and cloud deployment. And in terms of graph models, property graph models have dominant support. On the graph LLTP side, the graph query language different vendors use kind of reflect the chaos I talked about earlier. On graph LLTP type of workload, graph visualization is absolutely useful. So most of the vendors also have very strong visualization support. On the transaction side, most of them have some level of transaction support, and some even have asset guarantee. On the graph OLAP side, I have to say the support is relatively weak than graph LLTP, but 3 companies stand out: TigerGraph, Neo4j, and Oracle, because they have a large number of built-in algorithms. In terms of scalability, most of the vendors also have scale-out support. So let's take a look at the graph solution space. So one way to look at the solution space is native graph databases versus hybrid graph databases. So native graph databases have very specialized query engine, storage engine, everything built from scratch just for graphs. So because they are highly optimized for the workload they support, they tend to excel in performance, but they also tend to have higher engineering costs because they build everything from scratch. On the other hand, the hybrid graph databases have a query engine or query capabilities, but resort to an existing backend data store for data storage or data persistence. And all actually many graph databases fall into this camp. Because they actually leverage an existing data store, so they have much faster development time, and also they can get many things for free from them, such as transaction support, such as HADR or scalability. Of course, the performance-wise, it may not match a highly optimized native graph database, but I think it also depends on the actual implementation. Another way to look at the graph solution space is graph-only databases versus converged graph databases. So all the native graph databases obviously fall onto the graph-only database camp. And most of the hybrid graph databases are converged database, or sometimes people call it the multimodal databases. So graph-only databases, obviously, they only support graph workload. And that is also sometimes is a disadvantage, because sometimes you have mixed workload. And if you look at Neo4j and Tiger Graph, they often have in their user manual, they often have dedicated chapters on describing how to do data import and export. On the other hand, the converged database, because they support polyquery languages or APIs on the same data, sometimes it actually, if you consider the end-to-end pipeline of heterogeneous workload, it can actually have some advantage. And I want to elaborate a little bit on the advantage of converged database solutions. So eventually, the converged database solution solves the fragmented database problem, right? So seldom do you have only a homogeneous workload that's just about graph. Graph is often mixed with SQL, with ML together. So within this fragmented database world, you have to move data from one system to another system for your pipeline. Whereas in the converged database world, you have the polylanguage API and the shared data. So essentially, you just view the data in the way that is needed, right? So a SQL, whether it's a SQL, graph, or ML, can work synergistically on the same store on the same data. And no data transfer or transformation cost is needed. And in some graph databases often support, graph queries on the original data from the operational store. That means there's no schema change, no secondary copy of the data. In that case, the advantage is that you're not disturbing any of the existing relational applications, and also transaction updates to the operational store can be visible to the graph analysis in real time. Of course, the other set of advantage comes from the fact that it's built on top of an existing data store. So quite often you can get a transaction support for free, access control for free, compliance audits and regulations, temporary support, scalability, HNDR, etc. So now graph benchmarks are very important to evaluate different graph databases. And in the graph databases are relatively new compared to relational databases. So there's not a, widely accepted standard yet. And there are a lot of graph benchmark efforts in the community today, such as Graph 500 benchmark, HPC Scalable Graph Analytics benchmark, LinkBench, Open Graph benchmark, and LDBC benchmarks. Notably, I think the LDBC benchmark is the most comprehensive and also widely used in the market. So probably the closest to a standard. Tiger Graph and Neo4j have published white papers and blogs about conducting LDBC experiments. I don't think they're audited, so I will not say they're LDBC benchmark results. And it's interesting, there's also back and forth, they're reacting to each other's benchmark results, non-audited benchmark results. So one thing is there's a lot of research work going on in the research community about comparing different graph databases. This line of research is highly valuable, but what I see is they often propose their own benchmark, and the studies from the conclusions from the different studies often are not consistent. So I think going forward, it would be nice if all future performance studies adopt, more standard or widely used benchmarks such as LDBC. That would be more useful for the industry. Now I'd like to talk a little bit about the opportunities and directions. So clearly there's a growing market for graph databases. And right now the graph-only vendors are leading in performance and the algorithm support. But I think there's still some opportunities for other vendors and new vendors to catch up. I think for graph-only vendors, they need to pay attention to the data import and export, and that's going to be something that I really need to pay attention to. And we also see major cloud vendors are investing in graph database space, and their advantage that they own the whole data stack, right? They have, including the operational stores where most of the source of truth are from. And I think for them, taking advantage of the whole stack is going to their winning recipe. So finally, I want to give my 2 cents for researchers who want to actually have more practical impact. I think if you want to have more direct practical impact, it's better to use widely adopted graph models and languages and benchmarks, not to invent any new ones. The other thing is I feel like the graph research community has focused a lot on fancy algorithms and performance, but there are also other very important, equally important, also practical issues that the graph industry need help on, such as multi-tenancy, access control, security, compliance, end-to-end pipelines with mixed graph and non-graph workloads, and dynamic graphs. So that's all I have to say about graph databases. With that, I'm open to questions and suggestions.
Please look up.
Thank you, Yuanyuan, for great talk. Actually, you mentioned about the solution space of Converged DB. Well, I personally like the solution because basically you can do graph queries directly on SQL. Don't need to do the ETL stuff. However, what I'm wondering is how you actually do that on the relational data directly, because graph database in graph queries you do a lot of like searching the adjacency list. Without an index, that would be pretty inefficient and drive our customers away. So is there any practice at Microsoft you can mention to us? Thank you.
Actually, I think that today there are a lot of vendors are doing the converged databases. Oracle, what Oscar said earlier today is one of the examples. They are basically built it directly on top of relational database. They translate everything back into SQL. Back in IBM, we did the same thing. We basically just support a graph layer on top of DB2, and everything is translated into SQL queries. And in Microsoft, the SQL graph solution is the same. So the data is stored in SQL store, and there is some extension in the language to support the match statement. But at the end of the day, everything is executed in the relational engine. And we did some experiments back in IBM. I mean, it really depends on the actual implementation. We did a lot of optimization, including compiling time optimization as well as runtime optimization. We could get close to the same ballpark to some of the state-of-the-art graph databases. So.
Thank you very much. This was a really nice talk. And I agree with most of your comments, but I have to disagree one of them, right? So don't invent new benchmark. It was definitely a wrong statement. And I think your intention was not really preventing the new invention, right, but just supporting the community effort, which I would agree. But obviously, if you're lacking behind, we have to go do those things.
Yeah, I think what my comment is that if you want to have a direct impact and try to adopt an existing benchmark or improving on the existing benchmark, like the talk in earlier, but not to just having too many fragmented efforts. I think we need to have an aggregated effort. Otherwise, it's just another chaos. Yeah. Yep.
Just a quick comment about a couple of points in your sort of comparison table on the slides, because I think they're a little bit outdated in one respect. Both AWS, Neptune, and TigerGraph have implemented OpenCipher. And so the table has got more people doing Cypher. That's become a kind of de facto standard to a significant degree. And I think that this goes back to the comment from this morning that GQL builds on the PGQL Cypher kind of history. And that really means I think we're sort of already beginning to see more passage towards that sort of standards future. It's a detail, but for the future editions.
It could be, yeah. Okay. All right, thank you.
All right,